Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking in a lot more detail at the ideal gas law. So to do this, we're going to go ahead and take our three individual simple gas laws and combine them to a net ideal gas law. So we're going to go ahead and start with the Avogadro's law. So this means more moles I have, the more volume. Should hopefully make sense. We also have Boyle's law. So as I increase the pressure, the system will compress, which should hopefully make sense, and the volume will decrease. We also have Charles' law. I heat a system, it gets bigger. Fairly straightforward. Now, when we tie all of these together, what we find is that pressure and volume should be on the same side of the equation, but on the opposite side as moles and temperature. And this leaves behind one last variable, R. And it turns out that this is the ideal gas constant, which we've encountered before. So a good way of thinking about an ideal gas constant from this point perspective is that it is more or less going to encapsulate all of the individual constants we had from Avogadro's, Boyle's, and Charles and put them together. And this was originally empirically determined. So you do a measurement, and this is the variable, this is the constant that pops out that lets us convert in between these various units. Now, the ideal gas law is incredibly useful as it's going to relate these four variables. So it turns out as long as we know three, we can get the fourth. Now, one of the things I do want to emphasize when using the ideal gas law, only use absolute temperature. If you try and use temperature in any other unit, you will run into problems. So again, make sure temperature is always in Kelvin. If you try Celsius, it won't work. So a good way I like looking at is when it's okay to use Celsius, can you plug in 0 and it makes sense? So if I plug in a temperature of 0 Celsius, I shouldn't have a volume of 0. So that doesn't work so much. However, since Kelvin can never get down to 0 degrees, it can only approach it very slowly, we'll never get to a system that has 0 volume. Now, with the ideal gas law, one of the big things that's going to be very useful is I can often measure 3 of these variables and then determine the fourth. So I can measure temperature, pressure, and volume, and then I know exactly how much gas I'm working with, or I can pump gas into a known volume and temperature and back out the pressure, or so on and so forth. However, in order to actually determine these values absolutely, we need to have the ideal gas constant, so this R. Now, one of the things you should watch out for is there are a lot of different units that R can possess because, well, N will always be in moles and temperature will always be in Kelvin. We've got a lot of different units of pressure and volume to work with. So whichever unit of the ideal gas constant you use should be based on the pressure and volume you're working in. So for example, we have a value of 0.08206 when we're working with liter atmosphere, or 0.08314 for a liter bar. You can also convert this into liter torr or cubic decimeters times kilopascals. All of these are fair units, but the two major ones we're going to tend to use the most of is liter atmosphere and joules Kelvin when we're doing essentially energy-based properties such as a kinetic gas. However, it is possible to convert all of these units back and forth, and you'll note that there's some certain unifying themes based on the relationship in between pascals, bars, and joules, which we'll talk about a little bit more detail later this semester and a lot more next semester. However, one of the problems when we're working with the ideal gas law is if I'm working with an atmospheric sort of sample, we really can't measure how many moles of gas are in the atmosphere, nor do I want to measure the size of it. So if I'm trying to work with a large sample, I don't want to use size intensive properties. I'm going to want to use size extensive ones. So ones that don't depend on the size of my sample. So one of the good choices is called molar volume. And we can rearrange our ideal gas law to get volume per mole. Now, one of the important things to remember is that if we take the ratio of two size-intensive properties, this gives us a size-extensive property. So it doesn't matter exactly how much gas I'm working with. As long as the temperature and pressure are constant, a gas will always have the same molar volume, or 1 mole of gas will always occupy the same volume. And this is going to make it very useful for comparison of essentially the concentrations of different gases. Now, one of the things that is often done is you can go ahead and try and figure out exactly the exact size occupied by gases under fairly normal conditions. So in order to get an idea of what acceptable molar volumes are, it's nice to have a reference condition. So the go-to reference condition is called standard temperature and pressure. So this is going to be under 1 atmosphere, so that's our standard pressure, and 0 degrees C, so that's going to be our standard temperature. So if we go ahead and plug in 273 Kelvin and 1 atmosphere, we'll pop out a volume of 22.4 liters. So if you've got a 1 mole of nitrogen at freezing temps, it's going to occupy a little more than 22 liters of volume. So about the size of a good sized aquarium. So that's actually a lot of volume for only 32 grams of oxygen. So this is a very useful thing to try and keep in mind when we're talking about how concentrated a gas is. However, we can also relate it to other more classic concentrations, such as it's also possible to determine the molarity of a gas simply by, again, rearranging our equation to get moles over liters. So if we do this, we can back out to a way to calculate the molarity of the gas, and just like molar volume, which again will be the inverse of molarity, it only depends on the pressure and temperature. The higher the pressure, the more concentrated the gas is. The lower the temperature, again, the more concentrated the gas is, which should hopefully make sense because you compress a gas when you freeze it or pressurize it. However, a lot of times, instead of trying to measure molarity, we often measure the density of a gas. And in order to do this, we can multiply the left side of our equation by molecular weight. Now, to logic this out in terms of units, this is going to be moles per volume. Then we can multiply this by mass per moles. And the moles end up canceling out, and we end up with mass per volume. And that's another way of talking about density. So if we multiply the left side of the equation by molecular weight, this means we also have to multiply the right side by molecular weight. So if we're working with a pure gas, we can figure out its density as long as we know its temperature, its pressure, and its molecular weight. Again, higher pressure gas, more dense; colder gas, more dense; heavier gas, not too surprisingly, more dense. So we can allow the conversion of density, temperature, and pressure for any known gas of a single identity. However, trying to determine the density of a gas that's made of 2 or more substances gets a little bit messier. So next time, we're going to be diving in what to do when I have a mixed gas sample as we bring up Dalton's law. Until then, take care.